Thank you very much. It's a great pleasure to be here in Moscow. This is actually my first trip to Moscow, and I have wanted to come here for all my life, and so it's a very exciting time for me, and very exciting that I can give this lecture. Here is a quotation about the great Hungarian mathematician Paul Erdős by one of his collaborators, Fan Chung, a woman mathematician. She is now at University of California in San Diego. And I think, you know, in mathematics, we think it is absolute, and it is absolute, but the spirit is very, very important. And I think this speaks about the spirit of Paul Erdős. Let's see. Whoops. Okay. There. So this is my title. So this I like to call Erdős magic. Erdős worked in so many subjects in mathematics, but I will speak about one area that's called the probabilistic method, is the official name, but more and more I like to call it Erdős magic, and the idea is you want to show that there exists an object with some property, and you show that the random object has positive probability, then the object absolutely, positively, definitely exists. If the probability that it is good is positive, then it has mathematical existence. And that is the magic, and we will see examples. But in modern terms, often the examples we'll have today, it is not simply a random object. It is a random algorithm that will do something. And if we can show that the random algorithm has a positive probability of being successful to create the object, then again the object must exist. But it leaves the question, how do you find the object? How do you find the object? Now, if the probability of success is greater than 1/2, you make a randomized object. But what happens if the probability of success is exponentially small? Well, these are finite problems, so of course you can try everything. But what about an efficient algorithm? Well, this is a difficult problem, and I will show today two recent successes about the problem. So the first part involves the Lovász local lemma, which was found in 1970, approximately 1970, by the Hungarian mathematician László Lovász. But I will only give one example. If you're familiar with a lemma, you will see it's more general. But I will give an example in KSAT. So we look at Boolean expressions. We have n variables, x1 through xn. K is fixed. We have clauses consisting of k variables, the disjunction, and an instance of KSAT is we want all the clauses to be true. Of course, 3SAT is the basic NP-complete, the famous NP-complete problem. And now, let us define that two clauses overlap if they have, if they have a common variable, either with negation or not. So that means overlap. And now the Lovász local lemma in this particular case assume each clause overlaps only D other clauses, and assume that E times D times 2 to the minus K is less than or equal to 1. This can be made a little bit more precise. E is 2.718. Then the Lovász local lemma says this is satisfiable. That is, there exists true-false assignment for the xi's. So I won't give the original proof of Lovász, but I will give the new proof. So as an example, if we think asymptotically, fix, for example, k equals 5 and d equals 10. So each clause is x1 or x2 or not x3 or x4 or not x17, a clause of length 5, and you assume each clause overlaps at most 10 other clauses, and then asymptotically we let the size go to infinity, and the Lovász local lemma says there exists a satisfying assignment, but the question is, how do we find the satisfying assignment with an efficient algorithm? And the original proof of Lovász did not give an algorithm. It was a probability proof, extremely ingenious probability proof, but the original proof did not give an efficient algorithm, but I want to give a method due to Moser. Interesting, when he discovered this, he was a graduate student at ETH in Zurich. And he discovered this idea, but then it was worked on Gabor Tardos, Wes Pegden, Mario Szegedy, Szegedy student Kolipaka, and the approach I will give is due to Don Knuth, the famous author, computer scientist. But the original idea was Moser. So here is the algorithm. I like to call it the fixit algorithm. So first, we're given the clauses with this assumption. Okay, so first we randomly assign true, false. Then, well, if it works, we stop, okay? So suppose it doesn't work, so some clause is false. We select one of the bad clauses in any method we want. Maybe they're in lexicographical order, any method. In fact, we come back to this later, this part. We select one of the bad clauses, and then the variables in that clause, we reassign true, false. We flip a new coin. We reassign true, false. But what I like best about this algorithm is step 4. Because what is step 4? There is no step 4. We're done. That's the algorithm. That's the whole algorithm. The algorithm is done. But of course, we are theoreticians. We want to prove. We want to prove that the algorithm works. So that is, we want to prove that the algorithm will stop in finite time, because it only stops when we found the assignment. And in fact, it will stop in a reasonable time, but I'll leave that out. So we run this randomized algorithm, and we create a log of which clauses are being reassigned. sorry, I think for many of you, English is not your first language. The word log has many meanings. In a ship, there is a book where you keep, the captain writes down everything, and that's called the log. So that's the meaning I want of the word. So here we keep a log. So for example, here are the variables x1, x2, x8, and first we change x1, the clause with x1, x2, and x3. I don't say where are the negations, some clause with x1, x2, x3. So here are the different clauses, at least which variable, and suppose first we change clause A, then we change clause D, then we change clause C, then we change clause F, etc. So, but a priori, the algorithm could go on forever. The algorithm, in fact, if there's no satisfying assignment, it must go on forever. Okay. Now, maybe you are too young to know about Tetris. Does anybody know what Tetris is? Yes, okay. I thought you were too young for Tetris, but there's a new version. Okay.
This year.
Yeah, for this year. Oh, good. Okay. This is the old version. This is Don Knuth plays Tetris. So here is some word, some prefix. Okay, and now we play Tetris. Here is A. We put it down, and then we put down D. Well, C we have to put on the next level, and then F we have to put. Now notice A and D, the clauses have different variables. They have different variables. And then we put down, now they don't have to be consecutive. That's just, they're only consecutive because it's convenient to, you could have a clause X1 or not X2 or X7. That's perfectly fine. So the consecutive, it's just convenient. Then you have E, then you have C, then you have B, and then you have F. Okay, well that's nice. But now we look at F, at the last F, and we look at what is supporting F. So we see we call it pyramid. The pyramid is those things that are holding up the last F. So for example, this A, because this A holds up the C, which holds up the E, which holds up the F. So now, first we had A, D, C, F, E, C, B, F, but the pyramid is A, D, C, F, E, F. Okay? A nice semi-group here with the words on, we have a finite number of clauses. We're looking at words. We have a nice semi-group here. Okay. Now, a simple statement, when you run the algorithm, you look at the prefixes for the word. I mean, a priori, it might be infinite. It might be infinite. You look at the prefixes, A, AD, ADC, ADCF, etc. But for each prefix, you take the pyramid. So the pyramid of AD is simply D. Okay, and so now you get the pyramids of the prefixes. But these pyramids of prefixes are all distinct. Well, why? Because the last letter is in it. So if they were the same, they would have the same last letter. Well, maybe you have F, and then later on you have F. But if you take the prefix of this F, it includes the pyramid of this F, it includes this entire pyramid. So they're not equal. They're not equal. So a little bit of logic that the pyramids of the prefixes are distinct. And so now we look at the T log was the number of steps, the length, it's not really time, but it's the how many times you make the while loop. And we look at this, and its expectation for every possible pyramid S, we have the probability that S is a pyramid. So this is by linearity of expectation. Because T log is the sum over every S of the characteristic function that S is the pyramid of a prefix. So therefore, we get this. Now, actually, let's take a simple prefix, A. What could be more simple than that? What is the probability that A is the pyramid of a prefix? It actually depends on which clause you choose when you have a choice. So, for example, suppose initially both A and D were both bad. Well, if you choose A, then A is the first letter, so the pyramid of A is A. But if you choose D, then suppose that both A and B are bad. Suppose both clause A and clause B are bad. If you choose A, then A is a pyramid of a prefix. But if you choose B first, then A is not the pyramid of a prefix, because maybe you do change A, but its pyramid has B. But what I will look at, is actually an upper bound for this when I say the probability that ADC is the pyramid of a prefix. What I mean, let's look at the worst case. Suppose we say that clause A is bad at the start, and then we change it, and then clause D is bad, and then we change it, and then clause C is bad, and then we change it. Now, how do we analyze randomized algorithms? I think this is a very powerful idea. Maybe if there's one thing you take with you today, this is a powerful idea for analyzing random algorithms, which is you pre-process the randomness. So I want to say at the start that each variable xj makes a countable number of coin flips. True, 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 false, false, true, true, false. A countable number of coin flips. And that is your probability space. And then after that, the algorithm is deterministic. The coin flips 0, that's what it is. And if it needs to flip a coin again, we know what the coin flip is. So all the randomness is at the beginning. Sometimes this is called fictional continuation, because you flip a coin countably many times, but you're not going to use them. You're not going to use them, but you have them. So now, here is the critical thing, and I just do it with this example, but it's very general, is what is the probability that A is bad and then C is bad? Well, A and C overlap, but they're still independent. They're still independent. The probability that A is bad and then C is bad is 1/8 squared. They're still independent because A must be bad on the first coin flip, and then C must be bad on the first coin flip of 4, the first coin flip of 5, and the second coin flip of 3. But the second coin flip of C is independent from the first coin flip of A. So this is very powerful. Even though A and C overlap, the probability that first A is bad and then C is bad is 1/8 squared, as if they were independent. And in general, where did this light go? Whoops. There. And in general, if the pyramid has t, it's 2 to the minus k to the t. And now there's a very beautiful algebra. If you like algebra, there's a very beautiful algebra. In fact, it was studied by Fawata and other people just because it's an interesting algebra. You remember there are only a finite number of clauses, so you have a free semigroup on the clauses, the set of words on those letters. But you say that they commute if there's no overlap. And notice here that ADC and DAC give the same Tetris pattern, So the event that you start ADC and the event that you start DAC, it's not only that they have the same probability, they're the same event. They're the same event in terms of that A is false with coin flips 1, 1, 1. D is false with coin flips 1, 1, 1. C is false with coin flips 2, 2, 2. And that's the same for ADC and DAC. So when we sum over all pyramids, we do it in this algebra. Two words are equal, we have commutativity, a limited commutativity, which is a very interesting algebra. We have a finite set of letters, and we look at the free semigroup on those letters, and certain pairs commute and other pairs do not commute. And then, this is the way Don Knuth does it. We sum over every possible pyramid in the algebra the probability of getting that pyramid, which is 2 to the minus k to the length of the word. And suppose that sum is finite. But this sum is an upper bound for the expected value of the length of the pyramid. And actually, in most cases, if this is finite, it's not too big. So we actually get efficient algorithms. So now, from modern Erdős magic, if you have property Knuth, then the algorithm must stop in finite time. With probability 1, it must stop in finite time. Actually, all we need is that with positive probability, it stops in finite time. And therefore, we have satisfiability, and therefore fixit takes expected time at most this sum. Now there's some very interesting problems in algebraic combinatorics, which if you like algebra, this is a beautiful, beautiful general problem. It has a beautiful solution. Given any finite alphabet, and given that certain pairs commute and other pairs do not commute, and then given, well, here to each letter we give probability 2 to the minus k, but more generally we could give to each letter a probability, and we could ask, is this sum finite or infinite? So that's a beautiful question, and it turns out, this is the part I skip. Why am I having trouble with finding the red? Where did it go? Is it here? But a partial answer to this question is the result of Lovász, that if E times D times 2 to the minus K is less than or equal to 1, then, where did it go? I can't find where's the red dot? It's very, whoops. Oops. Yeah. Oh, okay. Oops.
It's below. It was below.
Ah, it was below.
Now it's
Oh, now I see it. Okay, it has to be higher. Okay, and so, well, we need this result in algebraic combinatorics, but that's only mathematics. But very pretty mathematics. Very nice generating functions. Very, very interesting, and we get this result. Let me mention, this is my own thought about it. This is an idea in complexity. I've spoken to Vigderson and some other people, and I think it's an interesting idea. Let's look at this step here. I said you could make any method to select this, but actually it's stronger than that. Imagine an adversary that's prescient. Prescient means it knows the future. It knows the future. So suppose, remember, each xj selects true, 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 false, false, true, 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 a countable number. Suppose the adversary knows all the values. So it knows the future. So when it says, take clause W, it knows exactly what the next answer is going to be. Even so, if you look at the argument, it still doesn't help. So this algorithm works even against a prescient adversary, which I don't know. I think it's interesting. Okay, so that's part one. And so I'm halfway, that's good. And now I want to give a result of my own from 1985. So this was a problem of Paul Erdős. So you have, first I give it in combinatorial form. You have n sets on n elements, and you want to color the points +1, -1, or red and blue, if you like. And then for any set, you add up the colors. So that means red minus blue. And what you want, and we want this to be close to 0. We want this to be close to 0. And my theorem, this was a conjecture of Paul Erdős, and I proved it in 1985, was that there exists such a coloring, and all, the important word is all of the discrepancies are less than or equal to 6 squared of n, but 6 is not really 6, it's 5.3 or 5.1. The important thing is that it's an absolute constant, And so I was I'm still very happy. I think it was the best. In my whole life, this was my best single theorem, and I was very happy with it. And immediately, when I looked at my proof, it used the pigeonhole principle. So I thought, well, the pigeonhole principle, you can't make an efficient algorithm. So I conjectured that you couldn't actually find the coloring with an efficient algorithm. Now, I always thought that if I reached a certain age, once I reached 1 million, Now I'm 1,100,000. Once I reached 1,000,000, that the best thing that could happen to me would be if one of my theorems was proven. Excuse me, that would really be good. The best thing would be if one of my conjectures was proven. But actually, I was wrong. Something even better happened, because in 2010, in fact, I was exactly 1,000,000 then, Nikhil Bansal, at that time at IBM in Yorktown Heights, US, now in Urandom in the Netherlands, and he did find an algorithm using semi-definite programming. And more recently, Shekhar Lavit and Raghu Meka also found an algorithm, and I want to give the idea of their algorithm. So first, let me turn this into a vector formulation. If you think of the n sets on n elements, you make the incidence matrix, and you look at the row vectors, and you'll see that this is a generalization. So we have n vectors in n space. All of the coefficients, all of the coefficients are between +1 and -1. For the sets, they're all either 0 or 1. And now there exists an x. Oh, and then we have an initial value z, but think of z equals 0. And now we want to find an x with +1 or -1. So this is the coloring. If you think of the incidence matrix, you have the n sets and the n elements, and you have the row vectors, and then this x is color of 1, color of 2, ... color of n. So this is the coloring, and ri dot x is less than or equal to k squared of n. K will be 6, but for us, the important thing is k is an absolute constant. And again, the crucial word is all. Now, the natural thing, let's just think of z equals 0. The natural thing is to pick x at random. And if you pick x at random, x dot ri is Gaussian, and its standard deviation is at most square root of n. So if you take k equals 6, the chance that it is not between 6 root n and -6 root n is very small, but it's a positive number. And we want this to be an absolute constant, and we want where n is arbitrarily large. So the problem is outliers. That is, if we pick the x at random, there will be this tiny percentage of values I such that x dot r sub I is bigger than 6 root n. Maybe 1 in a million, but still a positive proportion. And what we want is that there be 0. That's our object. So actually, I will just do phase 1. I will use the idea of floating colors. I think of the color as a real number between -1 and +1. Originally, the colors are all 0, so that's good. All the discrepancies are 0, but we haven't done anything. And at the end, all of the colors are +1 or -1. But in between, they are real numbers that are moving around between -1 and +1. And they're going to move in a kind of Brownian motion, we'll see. Well, it will be discrete because it's an algorithm, but I think of it like Brownian motion. Okay, so actually, because it's a finite algorithm, take, for example, epsilon equal 1 over n, and if xi becomes bigger than 1 minus 1 over n, then it's frozen. Because if you change it then to 1, it's only going to have a small effect. Okay, so because it's a finite algorithm, we will just freeze xi if it becomes bigger than 1 minus epsilon or less than minus 1 minus epsilon. And at the very end, if it's bigger than 1 minus epsilon, we just change it to 1, and that's a small error. Okay. And we're going to make steps where the steps will be small because we always want the numbers between minus 1 and plus 1. So we don't want to jump outside the cube. We have this cube minus 1 plus 1, the n-dimensional minus 1 plus 1 cube. We start at 0, we're moving around, but we don't want to jump outside, so we make sure that each step is maybe n to the minus 4, so that we don't jump from near the boundary to outside the boundary. Okay, so these are some technical things. And again, think of z as 0, and look, we can normalize rj by n to the minus 1/2. So at least in phase 1, we only need that the rj's have Euclidean norm at most root n, and we let lj be this value. So notice n to the minus 1/2 rj is at most a unit vector in the Euclidean norm. But again, the problem is the word all. We want all of the lj's to be less than or equal to k. We want no outliers. Okay. So suppose we're in the middle of the algorithm, and we have some value in phase 1. I'll only do phase 1. We're in the middle of the algorithm, and we have a value x, and now I want to tell you how to move. Well, I'm going to make a random move, but a controlled random move. Only certain directions are allowed. So what I say, and here are the 3 rules. If xi is frozen, it's frozen. So that we're not going to move. Okay. But this is only phase 1, so that's n over 2 conditions. At most n over 2 conditions. Okay. Not bad. Technical condition, actually, Lovett and Maka don't do this, but I find it convenient. Move orthogonal to where you are. Okay, that's only one condition. These are linear conditions, So move orthogonal to where you are. But here's the important one. Look at we have these LJs, so we have n of them. Look at the most dangerous ones. That is, the ones that currently have, where the LJ has the biggest value, the biggest absolute value. And look at remember LJ is, we take the rth vector, r sub j dotted with x. So some of them will still be small, but some of them will be getting big. Look at the most dangerous n over 4 of them, and I say, those we are going to freeze for the next step. Not forever, but for the next step. We're going to freeze because we're going to insist that we go orthogonal to those n over 4 r sub j's. So if we go orthogonal, that means LJ is not changing, Okay. So this defines a hyperspace of possible moves V, and it has dimension D, which is bigger than roughly n over 4. The minus 1 isn't important. Okay. And now we make we do a Gaussian on V. We do a standard Gaussian on V. So V has dimension D, so it has an orthonormal basis. So in that orthonormal basis, it just looks like R to the D. So we just go Gaussian in each direction, and we normalize by square root of D. And so now we get the D-dimensional Gaussian with the expected value of the norm of G squared is now 1. Not only is the expected value now 1, but actually, I mean, it's really close to 1. I mean, this is a chi-square, and there's some standard things. The probability that it's very different from 1 is extremely small. Okay. And now what we do is we make our move. We go by G, but we only go, the delta is like n to the minus 4. Of course, to make an efficient algorithm, we want delta to be as big as possible, but think of delta as minus n to the minus 4, and we just go in that direction. And we go in, and then we keep on going and going and going until phase 1 is finished. Okay? So let's see what happens. So now the crucial thing, if you look at what's happened to Lj, we've moved by delta G, and so we've added delta times this unit vector, or maybe smaller, dotted with G. But you know, the multidimensional Gaussian is a beautiful thing. And the beautiful thing is there's no direction. All directions look the same in the multidimensional Gaussian. So it doesn't matter in which direction. Actually, the only thing that matters about R sub j is its projection onto the vector space V. Is how big its projection is onto that vector. Because then it doesn't matter what direction it is. So even take the worst case, even assume that it's completely inside of V. But wherever it is, this additional value, this value, the random, Rj is not random, it's given. So this is a given unit vector, or subunit vector. It has a given projection onto V. Delta is delta, and G is random. But that means that this quantity is itself Gaussian. And it's Gaussian with standard deviation tau square, and tau square is less than or equal to the delta square, because we're moving delta. The delta will cancel out in the end. The delta squared times 1 over d from the dimension. The d is less than or equal to n over 4, so it's less than or equal to 4 over n times delta squared. Now here's a fun, now we stop for some fun. Let's go to Monte Carlo, to a mathematical Monte Carlo. So in my mathematical Monte Carlo, you start with 0 money, but you have an infinite amount of credit. You can go arbitrarily plus or minus as much as you want, but you only have a limited amount of risk. So what you do is when you go and bet, you say, I will risk 7. And what that means is that the outcome of that bet is a Gaussian with standard deviation 7. Okay? And so maybe it's plus or maybe it's minus. But it's a casino, so then you make your bet, and then you make your next bet, and you make your third bet, but it's your choice of the second bet can depend on the first bet. Okay. And actually, in this particular case, what I want to say is that the teeth bet you can risk at most sigma t. Suppose that on the teeth bet you could, and you might think of all the sigma t's equal 1. So on the teeth round, you can say I risk 1, or you can say I risk 0.9, or you can say I risk 0. You can say I've had enough. I'm going to stop now. And then let sigma squared be the sum of the sigma sub t squareds. So if at each time you risked sigma t, then the final outcome would be a Gaussian with a variance sigma squared. And the martingale, so this is a martingale, and the martingale theorem is that the probability that at the end that you are lambda standard deviations above the mean is 0. The probability that your lambda standard deviations above the mean is less than or equal to e to the minus lambda squared over 2. And this comes from, there are many, this is a nice exercise in martingales. One way is to use what are called Chernoff bounds, but mea culpa, mea culpa. It's my fault. Many years ago, I started calling these Chernoff bounds, and now everybody calls them Chernoff bounds, but you know they're really I'm just losing the word. They really go back. Sorry, I'll remember in a moment. Anyway, we call them Chernoff bounds. Actually, this is more powerful. This is a nice theorem by itself. We don't even need this. We only need the condition that the total risk, the total sum of the squares of the taus, is less than or equal to sigma, and then you have the Chebyshev. These are really I knew there was a Russian here. So these are really in Chebyshev, so they really should be called Chebyshev bounds. But 40 years ago, I started calling them Chernoff bounds for the American mathematician Chernoff, and now they're called Chernoff bounds. Okay. There's a simple extension of this, that the probability that the maximum is greater than or equal to lambda sigma is also less than or equal to e to the minus lambda squared over 2. And this is a martingale idea that's very powerful. Suppose you want to look at you want to bound the probability that the maximum is bigger than lambda sigma. You do the martingale, but as soon as you reach lambda sigma, you stop. You just say risk 0, risk 0, risk 0 for the rest of the time. So if you have one idea, one strategy, then you can change, but you want to look at, but what you're really interested is that the maximum value of x is greater than or equal to lambda sigma. You can look at the final value of x, you just change the martingale. As soon as you reach your goal, you stop. So this is a general idea for martingales, and you get this bound. Okay, so you have this bound. So now we do this, and you know, this is discrete, but you think when delta is going to 0, it's looking like a Brownian motion. So each time you are increasing the value by delta squared. Actually, this chi-squared distribution, but it's pretty much delta squared. You start somewhere in the unit square, but you stay in the unit square. So your Euclidean norm squared is changing by at most 4n. I mean, maybe it goes from minus 0.99 to plus 1 in each coordinate. So it's 4n. And so the time is at most 4n delta to the minus 2. Again, we use fictitious continuation. We say, let's set the time equal to this. And when phase 1 is over, we then risk 0 from then on. Okay, and now we look at Lj after step t, and we have a martingale, and it has this Gaussian casino because at each time the standard deviation is 4 over n delta squared. The total amount of time is 4n delta to the minus 2. The n and the delta squared cancel out, and sigma squared is 16. And therefore, the probability that Lj is bigger than or equal to k is less than or equal to this. At this point, it looks like we still have the same problem we had in the beginning of outliers, because this probability is small, but we need everything to be small. So how do we do that? Fortunately, we're almost done. So we make this, we select k, maybe it's not 6, but whatever it is, so that this is less than 0.1. And so therefore, we have that for each j, the probability to be an outlier is less than or equal to 0.1. And we define success to say that we have less than n over 5 outliers. And there's a positive probability of success, but everything, the brilliant idea is in the last step. We have a positive probability that there are fewer than n over 5 outliers. But remember that at each step, the n over 4 that were the most dangerous were frozen. So if we only have n over 5 outliers, we have 0 outliers. And that's it. And that's the idea. I mean, the only way is a single step it might jump over. But the single step is only small. So this is the idea, that if you have only n over 5 outliers, that you could have done right from the beginning, but you have only n over 5 outliers, but at every step you froze the top n over 4. N over 4 is bigger than n over 5. So therefore you have 0 outliers. Or the only way it can be an outlier is a single step. Once it gets over it, it's frozen forever. And so that does it. So I'd like to end with something else about Paul Erdős. I mean, he was certainly known for his mathematics, but he wasn't usually considered a poet. But there is one place where he was writing a letter to his longtime collaborator and friend, Vera Schoch. And usually the letters from Paul Erdős, they looked like the following. Dear Vera, let G be a graph and H be a, it went on and on. And the letter, most of the letter was like that. And then he signs it Paul. But in this letter, he put in a little PS. And, sorry. I'll skip this part. This was only phase 1. Phase S, there's some other stuff. Let me skip. But here's the nice little poem that he wrote, sort of a rough translation. The original Hungarian is actually nicer, but I like it very much. It is 6 in the morning. The house is asleep. Nice music is playing. I prove and conjecture. So I wish the same to all of you. So thank you very much.
Any questions?
Yes.
In the fixit algorithm,
Yeah.
you said that an adversary could, essentially eliminate randomness. Is it true? Does it mean that we could randomize it and we don't need randomness?
No. So the question was, could the fixit algorithm, could the adversary eliminate randomness? No, the coin flips are random. The coin flips are at least in this algorithm, the coin flips are random, and the adversary only gets to choose which clause to change. He doesn't get to change the
Okay, good.
randomness. Yeah.
Thank you.
But still, there's a good question. Can you make this entirely deterministic? Can you somehow make some specific choice of the true and false, a fully deterministic algorithm? That I don't know.
One more question, probably.
Yeah, one.
About the last algorithm, you said that it is polynomial. Do you mean that it is polynomial in expectation, right?
Yes. It is polynomial in expectation, but I didn't have an answer for the first algorithm. For this algorithm, you can de-randomize it. You can create a weight function when you have these martingale inequalities with the Chernoff-Chebyshev inequalities. It is possible to make a weight function, and so it is possible to make it into a fully deterministic algorithm. I didn't show it here, but it is possible. Yeah.
Okay, I'm sorry.